Hello everyone, and welcome back to CSAITTL. I'm your host, and today we are tackling one of the most elegant yet often misunderstood algorithms in the string processing world, Manacher's algorithm. This video is a core part of our ongoing DSA series, where we break down complex engineering concepts into visual mental models. Today, we are solving the longest palindrome substring problem, but we aren't just finding a solution. We're finding the optimal solution in linear time ON. I call this the mirror lake problem. If you look at the whiteboard, you'll see that if you already know the height of the mountain, you don't need to remeasure its reflection in the lake. We're going to learn how to use previous knowledge to expand our search faster and avoid redundant checks. Before we jump in, make sure to follow, like the video, and hit that notification icon so you don't miss any new upcoming deep dives on this series. Let's get to work. Let's define the challenge. Given a string like BABAD, we need to find the longest part of that string that read the same forward and backward. Here, ABA is a palindrome of length 3, and BAB is also a palindrome of length 3. We use brute force, checking every possible substring. We end up with ON cube complexity. This is a disaster for large data. If we use the expand around center approach, where we pick a spot and look outward, we get ON square. While that's an improvement, it's still slow because we repeat work. We might check the same character dozens of times for different centers. Our goal with Manacher's is to do this in exactly one pass, ON. We want to scan the string once and have the answer. This is the difference between a junior level solution and a senior level optimization. When you implement a standard palindrome search, you hit your first headache almost immediately, symmetry types. Palindromes can have an odd length, like ABA. Here, the center is clear, physical character the B. But what about even length palindromes, like ABBA? The center isn't a character, it's a gap between the two B's. In a traditional algorithm, you'd have to write two separate loops or two separate pieces of logic to handle these cases. It's messy, it's prone to bugs, and it's conceptually annoying. Manacher's algorithm solved this by hacking the string. We want a way to treat every potential palindrome exactly the same, whether it started as even or odd. We need one logic to rule them all. So here is the first hack, the transformation. We take our original string, say ABBA, and we insert sentinel characters, typically a hashtag between every letter and at the very ends. We also add unique start and end markers like a caret and a dollar sign to prevent index errors. Look at what happened to ABBA. It is now um, sign hash A hash B hash B hash A hash dollar sign. If we look at even palindrome ABBA, it is now centered on the hash between the B's. If we look at an odd palindrome like ABA within a larger string, it would be centered on the character itself. The result, every palindrome is now odd length. By adding these filters, we have created a new string where every center is an actual index in the array. This allows us to write one single, clean loop that expands around every index without ever worrying about even or odd symmetry again. Now we get to the heart of the problem, the mirror intuition. The mirror intuition, imagine we are moving through the string and we have already discovered a very large palindrome. We call this as the known palindrome zone. It has a center C and a right boundary R. If we are currently at index I and I is still inside that big palindrome zone, we can look at its mirror image, which we call as I dash, on the left side of the center. Because palindromes are perfectly symmetrical, the string around I should be a reflection of the string around I dash. If we already know the palindrome radius of at I dash is 3, then the radius at I is very likely also 3. We don't have to rescan those characters. We can simply copy the answer from the mirror and move on. This is the secret to moving from quadratic time to linear time. To turn this intuition into code, we need to track our state. We have our transform string t and the new array called p and the radius array. Pi will store the radius of the longest palindrome centered at index I. We have three main players. Center C, the center of the palindrome that currently has the furthest reaching right boundary. Right boundary R, the right edge of that C palindrome. Mirror index I dash. This is calculated as 2 times C minus I. As you walk I from left to right, we constantly check if we are still within the known universe defined by R. If we are, we look back at the mirror to see what we can skip. This board setup is what allows the algorithm to have memory of what it has already processed. Let's look at the flow of our main loop. For each index I in our transform string, first we ask is I greater than R? If yes, we are in the unknown zone. We have no history to help us. We set our initial radius pi to 0, and we must expand manually. If no, we are in the mirror zone. We can use our mirror. We set pi equals pi prime. However, we have to be careful not to trust the mirror past our known boundary R. After we get our initial estimate from the mirror, we enter the attempt expansion phase. This is a simple while loop that checks if the characters to the left and right match. Finally, if our new palindrome stretches past the current R, we update our C and R. We have found a new king palindrome that defines our known territory. Manacher's logic splits into three different specific cases. Case 1 is the most efficient, the mirror fits perfectly. In this scenario, the palindrome centered at the mirror index I dash is relatively small. It is contained entirely within the main palindrome, the one centered at C. If pi dash is less than r minus I, it means the symmetry is guaranteed to be identical at I. Why? Because the entire environment around I dash is reflected perfectly around C to the environment around I. We can set pi equals pi dash. And we don't even need to run the expansion loop. If we do O1 work here, we just copy the number and jump to the next index. This is where the massive speedup happens. Case 2 occurs when the mirror is too long. Here, the palindrome at mirror I dash, actually extends outside the left boundary of the main palindrome. Our mirror knowledge is only valid as far as the main palindrome reaches. We are blocked by R here. We can't guarantee what's happening outside that wall. So, we set pi to the distance to the boundary, which is r minus I. We assume this is the minimum radius. Then we manually expand starting from r plus 1 to see if the palindrome actually continues further. Even though we are expanding, we're starting from a very advanced position, which still saves us a massive amount of work compared to starting from 0. Case 3 is the simplest, beyond the horizon. This happens when our current index I is completely outside our known right boundary I is greater than R. This is like entering a new universe where we have no maps and no history. We have no mirror to look at because we have moved past the reflection to the left side. In this case, we simply set pi equals 0 and perform a full expansion from scratch. Once we find the palindrome at this new spot, we almost certainly update our C and R variables, because this new palindrome will define the next known universe for the indices that follow. Manacher's is a constant cycle of using history until it runs out, then building new history. Let's visualize this with a trace of ABABA. We transform it with our sentinels. Early in the string, at index 2, the first A, we find a small palindrome and move out our right boundary R. When we get to index 3, which is the hash, we expand and find the palindrome of radius 3. Our C moves to index 3, and our R flag moves forward to index 6. Notice the stick figure representing C moving right. as R moves forward. Our known territory expands. At this stage, every time we move I, we are constantly updating our bounds. We are doing work here, but notice that we are only ever pushing R to the right. We never move backwards, and we never recheck characters that are already safely behind us. Now look at the payoff. We are at index 4, the first B, but our C is at 3 and R is at 6. We check the mirror. The mirror of index 4 across center 3 is at index 2 now. We look at P2 and see the radius is 1. We look at case 1. P2 is less than the distance to the boundary. We didn't expand. We didn't compare any character. We just copied. We skipped checking 5 characters in the single step because we trusted the symmetry of the mirror. This is exactly how Manacher achieves this superlinear field. It's making big leaps through the data by leveraging the geometry of the palindromes. The common question in technical interview is, why is this ON if there is an expansion loop inside another loop? The answer lies in the gear visual. Think of the right boundary R as a ratchet. We only perform character comparisons when we are actively trying to push R further to the right. R never moves left. It's a one-way street. Since the string has a length n, R can only move a maximum of n steps total. Even if one expansion takes many steps, those steps are banked. The next few indices will likely fall into case 1 and be solved in O1. When you sum it all up, the total number of comparison is roughly 2n. That is strictly ON. The work is amortized across the entire string. As you implement this, don't trip on these common pitfalls. First, always update R. If your expansion loop discovers a palindrome at the ends at R and past it, you just you must keep moving C and R. If you forget this, the algorithm loses its memory and reverts to ON square. Second, coordinate mapping. Remember that you are working on the transform string T. To find the starting index in your original string, use the formula start equals I minus pi by 2. Be careful with integer division. Finally, bounds checking. Those sentinel characters like caret and dollar sign aren't just for show, they are the guardrails. They ensure that our expansion loop doesn't fly off the ends of the array and cause an index out of bounds error. Let's wrap up with the senior design cheat sheet. Transform the string with fillers to make everything odd length. Loop through every index. If you're inside the known boundary, mirror the value from the left. Expand manually only if necessary. Update your center and boundary if you have pushed into new territory. Manacher isn't just a trick of strings. It's a masterclass in a fundamental DSA concept, using past data to predict the future. I hope these visual deep dives help you master this algorithm. If you want more content on interview-ready DSA patterns, explore the CSAI TTL. For videos on segment trees, KMP, and more, comment below what complex algorithm would you like to see us simplify next. Thanks for watching, and as always, happy coding.